Hello everybody, good morning. Myself, Dr. Shubhankar Sen, Associate Professor in the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the fifth lecture of the second module of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's class, we shall elaborate upon the identification and location matrix arrays for multidimensional problems. We shall show the construction of ID and LM arrays for single degree of freedom and multiple degrees of freedom. To this end, we shall consider Poisson's equation of heat conduction using bilinear quadrilateral elements and the Navier-Stokes equations of motion using the same set of elements. Now, we shall illustrate the construction of ID and LM arrays in two dimensions. We shall consider two problems. The first problem will be related to the heat conduction problem, where we have only a single degree of freedom, or this is an SDOF problem. Next, we consider a multiple degrees of freedom problem in two dimensions. For example, we shall consider the construction of ID and LM arrays for the Navier-Stokes equations of motion in two dimensions. So, we begin with the SDOF case, considering the Poisson equation of heat conduction in two dimensions. So, let us consider Poisson equation of heat conduction in two dimensions. The strong form is K del square T plus Q equals to 0 on omega, T equals to G on gamma G, and minus K del T del N equals to Q0 on gamma H. So this is the strong form. We show a representative domain. This is omega. This portion we just identify as gamma G, and the remaining portion of the boundary we consider it as gamma H. So this is the essential boundary condition part, and the remaining portion which I am highlighting here, that is the Neumann boundary condition part. So let us consider for simplicity a square domain in two dimensions. So this is omega. Here K del square T plus Q equals to 0. We have the boundary conditions. So the right boundary, we treat it as the Neumann boundary. The top boundary, the left boundary, and the bottom boundary, we treat it as the essential and Dirichlet boundary. The corner points, they are the junctions of essential and natural boundaries, or they are common points, but the essential boundary condition gives the specified value of temperature. Because of this, these two conditions are considered as part of the essential boundary. So these are associated with the gamma G, these corners. Now let us discretize the domain in two dimensions. This governing equation, we can represent it as K into del 2T del X2 plus del 2T del Y2 plus Q equals to 0 in omega. When we discretize the domain, we use bilinear quadrilateral elements to make the mesh. So let us construct Cartesian structured mesh to discretize the domain. We just mark the x-axis and the y-axis. So this is the origin, 0, 0. Now this is the delta x, the grid size in the x direction, and this is the delta y, the grid size in the y direction. So we are using bilinear quadrilateral elements. Bilinear quadrilateral elements. I have shown one example. So the element is represented by the symbol small e. Now I am highlighting the nodal points. The element has 4 nodes. These are local nodes. The numbers are 1, 2, 3, and 4. We follow counterclockwise node numbering. It means we use CCW or counterclockwise local node numbering. Local means elemental. Node numbering. Now, these vertical lines and horizontal lines, these are the grid lines. So I say that this is a grid line, a vertical grid line, and this is, for example, a horizontal grid line. So we have families of grid lines, horizontal grid line. So the picture which I am showing here, that is a case of Cartesian structured mesh. Now, in this case, we have used 5 vertical lines and 5 horizontal lines to construct the mesh so that we have total 25 global nodes. Let us identify the global nodes. 1, 2, 3, 4, 5. These are the global node numbers. These are unique numbers. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and finally the last node in the mesh, that is the 25th global node. Now let us identify the elements. So this is element 1. We identify the element with a circle. Element 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So the mesh which we are showing here, it has 16 elements, bilinear quadrilateral elements, 25 global nodes. It is constructed of bilinear quadrilateral elements. So each element, it consists of 4 local nodes. So for this case, we can write numel E equals to 16, number of elements, numen P, number of nodal points, it is 25, number of element nodes, Nen equals to 4, number of degree of freedom or number of unknown per node. So this is, we can say, NDOF equals to NEN into IDOF. So NEN is the number of element nodes. Number of element nodes. Number of nodal degrees of freedom. Number of nodal degrees of freedom for this case, this is 1. We have only one unknown, temperature alone. So NEE for this case will be number of element equations equals to NEN into NDOF. So NEN is 4 and NDOF is 1. So we have total 4 equations per element. Now let us first construct the IEN array for this case. The IEN array is defined as IEN small a E equals to capital A. Okay, so we make the IEN table as E A 1, 2, 3. We have 16 elements. It is going from 1 to 16. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. Our local nodes, they are varying from 1 to 4. So this EN, this corresponds to the small a things. Namen P corresponds to the capital A things. So capital A, it varies from 1 to 25. E, it varies from 1 to 9. Small a, it varies from 1 to 4. These are the quantities. So small a, index for local node numbers, and capital A, index for global node numbers in the mesh. So our A is varying from 1, 2, 3 and 4. So let us construct this chart now. Six, 7. For this, I am making the boxes where I have to put the capital A values. So we already have the elements along the row and the local node numbers along the column. So in the box, we shall put the capital A values. So if I go back to the sketch, then for the first element, our global node numbers are 1, 2, 7, 6. So it should be 1, 2, 7, 6. Then again, if I go for element 2, it is 2, 3, 8, 7. 2, 3, 8, 7. Similarly, I can construct 3, 4, 9, 8. 3, 4, 9, 8. The construction is made based on, this is the numbering, local node 1, local node 2, local node 3, local node 4. So these are the small a things. Okay. So after 3, 4, 9, 8, then we have 4, 5, 10, 9. 4, 5, 10, 9. Similarly, we have 6, 7, 12, 11. 6, 7, 12, 11. Then 7, 8, 13, 12. 7, 8, 13, 12. 8, 9, 14, 13. 8, 9, 14, 13. 9, 10, 15, 14. 9, 10, 15, 14. 11, 12, 17, 16. 11, 12, 17, 16. 12, 13, 18, 17. 12, 13, 18, 17. For the 11th element, it is 13, 14, 19, 18. 13, 14, 19, 18. For the 12th, it is 14, 15, 20, 19. 14, 15, 20, 19. Finally, we are left with the topmost row where we are having 16, 17, 17, 22, 21. 16, 17, 22, 21. Then 17, 18, 23, 22. 17, 18, 23, 22. Next 18, 19, 24, 23. 18, 19, 24, 23. And finally, for the last element or the nominal element, we get 19, 20, 25, 24. 19, 20, 25, 24. So in the boxes, we are getting the capital A quantities or the global node numbers. So now we have identified the global nodes corresponding to every element and every local nodes. Next, we have to construct the ID array or the identification array. So for this case, our element level equation will be KE TE equals to FE. Now, in this element level matrix equation, this is element level matrix equation. We get it from the weak form. The size of the K matrix is 4 by 4 because we have 4 unknowns per element. This is Ke, this is T1e, T2e, T3e, T4e, and our Fe is F1e, F2e, F3e, F4e. So these vectors are of 4 by 1 size. So this gives us the NEE values number of element equations. So this T1e I can associate with the local node 1, T2e I can associate with local node 2, T3e I can associate with local node 3, and similarly T4e is associated with the local node 4. So we have the element level matrix equation where we are getting a 4 by 4 case for single degree of freedom case. Now we are ready to construct the ID array in the global sense. A small correction here. Here E is varying from 1 to 16. For an SDOF case, we define for SDOF ID array is defined as ID of A equals to P, where P is the global equation number in the final matrix equation system. Okay, if B it belongs to eta G, then P equals to 0. So eta G is the set of all EBC nodes and B is a set of boundary nodes. Now if we go to the particular problem, we see that we have num np equals to 25, the total number of nodes. Now our NDOF nodal degree of freedom equals to 1 or unknown per local node. So we can get maximum number of global equations possible, maximum number of global equations possible equals to num np into NDOF. So this is 25 into 1 equals to 25. But our B belongs to eta G equals to the number of essential boundary nodes. So let us go to the mesh, and if we count the number of essential boundary nodes, we find that at the top surface we have 5 essential boundary nodes, at the bottom surface we have 5 essential boundary nodes, on the left wall we have 3 essential boundary nodes. So we have 5 plus 5 plus 3, 10 plus 3, 13. We have total 13 EBC nodes. So we know the solution at these 13 nodes. It means that therefore solutions are unknown at num np minus B into NDOF nodes equals to 25 minus 13 into 1 equals to 12 nodes. Therefore, our global matrix will be of 12 by 12 size. Therefore, the number of global or assembled equations we define a variable maximum number of equations. So this is maxi q equals to capital P or capital Q equals to 12. So it means that for this particular problem, we can maximum solve 12 number of equations, or our assembled matrix will be of 12 by 12 size. Now let us construct the ID array. So for the ID array, we have to again construct the number of nodes and elements we have to show here again. So we are again making the mesh. In this picture, the right boundary is NBC, the bottom boundary is EBC, the left boundary is EBC, and the top boundary is EBC. Since T equals to G given on gamma G, we assign P equals to 0 or 0 equation numbers at EBC nodes. It means that our global equation numbering, it starts from the unknown nodes. So we can simply put the equation number 0 for the EBC nodes. So that we are doing now. Now, our unknown nodes, where we don't know the temperatures, those nodes we identified and we put the global equation numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we are getting a total of 12 equation numbers. It means that we already calculated that we should have a 12 by 12 global matrix equation system. So these numbers, what we are getting here, these are the global equation numbers. Global equation numbers P at unknown nodes. Now we generate the ID array as A versus IDA. So our 25 nodes are there. So it starts with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25 for all of the global nodes. Now we make the corresponding boxes, okay? Then we shall insert the global equation numbers in these boxes according to the above picture for the global equation numbers. So let us just complete the boxing. Now for the global node 1, this was the global node 1, equation number is 0. For global node 2, equation number 0. It means that up to the 6th global node, our equation numbers are 0. So these are all zeros. So our first equation corresponds to the 7th global node. This is that 7th global node. So we can write for 7, 8, 9, and 10 nodes, equation number 1, 2, 3, and 4. When you go to the 11th node, it is a Dirichlet node. So this is the 11th node, equation number is 0. Next 4 equations come as 5, 6, 7, 8. Now, at the up to 15th node we have made. Then when you go for the 16th node, this is the 16th node. This is an EBC node. Equation number is again 0. So our equation numbers are next 9. Then it is 9, 10, 11, 12. At the 21st node, the global equation number is 0. Starting from 21st to the 25th node, all are EBC nodes. So the equation numbers are 0. So from here we are finding that our ID array, it is clearly demarcating between the non-EBC equation numbers and the EBC equation numbers. Finally, we construct the LM array, for which the ID array helps a lot. For the LM array, we represent the ID array in terms of the element and the local equation number. The LM array helps us in performing the assembly. Just now we have shown that we have the element level equations KE equals to FE and summation over KE, where E is varying from 1 to NAML. This gives us the assemble matrix K, which for this case will be 12 by 12, or these are maxi Q things, okay? And similarly, the assembly of element level load vector from element 1 to the NAML, the last element, our NAML is 16. NAML is 16. This will give us the assembled load vector capital F, okay? So that is a 12 by 1 vector. So for performing the assembly, we simply use this capital K PQ equals to capital K PQ plus small k F prime B prime E. This expression, this is written in terms of the computer coding terminology. So this is an assignment statement. So as if we keep on adding and assigning the value to the left side. This is something like an assignment statement in computer coding. So this value, this is the initial value that we assign to the computer. This is the initial value. Now this capital P or capital Q, they are the maximum number. Capital P and capital Q, these are the maximum number of global equations or maxi Q things. F prime and B prime, they are the number of element level equations. It means that this quantity F prime, this will vary from 1 to NEE, and similarly B prime, this will also vary from 1 to NEE. NEE means number of element level equations. So I have already shown that in KE TE equals to FE, we have, this is KE, this is TE, and this is FE. So this is a 4 by 4 matrix equation system. This is 4 by 1 vector and so on. So we have 4 equations. So this is the first equation. And this is the last equation. So the last equation, last or fourth equation. So here for this case, NEE equals to 4 for this case. Now here capital P, it corresponds to F prime, and capital Q corresponds to B prime. F prime and B prime, the right hand side quantities, these represent local equation number index. Number index, it varies from 1 to number of element equations. In this case, it is varying from 1 to 4. And capital PQ, they are global equation number index. It varies from 1 to maxi Q. In this case, it varies from 1 to 12. So if we consider the diagonal terms of the coefficient matrix, then P equals to Q, then A prime equals to B prime. This is for the diagonal terms of the assembled matrix. For the diagonal terms. So now for generating the LM array to be used for assembly purpose, we have given all the prerequisites. Now we construct the LM array as, for SDOF problem, LM AE equals to capital P. Okay, so this LM array, it can be constructed by this chart or table. We have 16 elements. So E, it is going from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have 4 local nodes per element. So that is going from 1, 2, 3, 4. And it is having only 1 degree of freedom for every local node. It means that here it gives us the last index for NEE or F prime or B prime. So this is the product of I and A. This is the product of I and A. So I and A is 1 into 1. So it is 1. 1 into 2, it is 2. 1 into 3, it is 3. And 1 into 4, so it is 4. So now we are ready for this chart. Here, let us make the box first. So the terms within the boxes, they will give us the global equation numbers or capital P, capital Q terms. Okay. So to make this LM array, we need the picture which you have made for the ID array. So let us go for the first element. For the first element, our equation numbers were 0, 0, 1, 0. So we shall write it simply 0, 0, 1, 0. For the second element, it was 0, 0, 2, 1. So we shall get 0, 0, 2, 1. For the third element, it was 0, 0, 3, 2. 0, 0, 3, 2. For the fourth element, it is 0, 0, 4, 3. 0, 0, 4, 3. For the fifth element, it was 0, 1, 5, 0. 0, 1, 5, 0. For the sixth element, it was 1, 2, 6, 5. 1, 2, 6, 5. For the seventh element, it is 2, 3, 7, 6. 2, 3, 7, 6. For the eighth element, 3, 4, 8, 7. 3, 4, 8, 7. For the ninth element, 0, 5, 9, 0. 0, 5, 9, 0. For the 10th element, 5, 6, 10, 9. 5, 6, 10, 9. For the 11th element, 6, 7, 11, 10. 6, 7, 11, 10. For the 12th element, 7, 8, 12, 11. 7, 8, 12, 11. For the 13th element, 0, 9, 0, 0. 0, 9, 0, 0. For the 14th element, 9, 10, 0, 0. 9, 10, 0, 0. For the 15th element, 10, 11, 0, 0. 10, 11, 0, 0. And finally, for the last element, it is 11, 12, 0, 0. 11, 12, 0, 0. Now, the entries in this box, these are the capital PQ terms or global equation numbers. Equation numbers. P or Q, they will be 0 if the equation numbers do not belong to the same element. This is a very important point, important criterion. So here I mentioned that we use the LM array for performing assembly of the element level matrices and vectors. But this assembly can be performed with direct observation of the mesh without constructing the LM array. But the construction of LM array, it is very convenient in computer programming, and because of this, we shall follow the LM array method for the assembly procedure. Now, if we perform the assembly process, already we have written the formulas. So we have the assembly formula as capital PQ equals to capital PQ, this initial value, plus K, F prime, B prime, E. This is contribution from the element. contribution from element. Okay, so let us take some selective terms. We want K11. So what we do, our P in this case, when we are writing K11, our P equals to 1 and Q equals to 1 and P equals to Q. So in this case, we shall have A prime equals to B prime. So we write the initial data first, initial guess. Then we search element wise in which elements the equation number 1 is present. Then we see that our capital index 1 is present in element 1 corresponding to the third local equation number. So the contribution will come from the first element, third local node. So this will be K, A prime, B prime, E. Here A prime and B prime both are equal for diagonal term, and that is 3. So it is A prime 3, B prime 3 and E equals to 1. So the first contribution is K331. Then we search for the remaining elements. Again it is present for the second element. So contribution will come from the second element. In terms of second element, it will be K442 because A prime and B prime both are 4. So it is K442. Similarly, we search for remaining elements. It is not present at elements 3 and 4, but they are present at elements 5 and 6 and nowhere else. For element 5, the contribution will be K225. K225. For element 6, it is K116. K116. So this is showing the construction of the diagonal term. For example, now we consider one off diagonal term. So let us consider the term, for example, K48. Okay. So let us search in which elements 4 and 8 both are present. So in the first, second, third, fourth, fifth, sixth, seventh, it is not there, but we have it at the 8th element. Okay. So it is K48 plus and the 8th element 4, P is 4, so A prime is 2. So K element is 8, corresponding to P equals to 4, our A prime is 2, so we write 2. Now for 8, for Q equals to 8, our B prime is 3, so this is 3. So we are getting the contribution as K238. Now we again search for 4 and 8 together in the remaining elements. It is not at element 9, not at element 10, 11, 12, 13, 14. So it is not present. So this is the construction of the K48. Similarly, we can construct the other terms of the matrix. And I have told you KPQ equals to 0. Okay. So KPQ equals to 0 if P and Q belong to different elements. For example, let us check K19. So K19 equals to K19 plus. Now we keep on searching for equations 1 and 9 in the same element. It is not present in element 1, not in 2, not in 3, not in 4, not in 5, not in 6, not in 7, not in 8, not in 9, not in the remaining elements. It is not there. It means that K19 has no contribution from other elements, from any elements. So K19 will be 0. Similarly, we can construct the load vector. I can show this here. Fp equals to Fp plus F A prime E. Okay. So let us first consider F1. This is the initial guess, F1. Let us search for index 1. It is present here. So Fa equals to F A prime E. F E is 1 and A prime is 3. So it is F31 plus in second element, it is at the 4th nodal number. So it will be F42 plus we again search. It is not, 1 is not present in elements 3 and 4. It is then present at element 5. So this will be F25. And then it has another contribution from the 6th element. So if it is F16. So this shows us, so it means that our F1 equals to, I rewrite this expression, F1 plus F31 plus F42 plus F25 plus F16. Okay, so in this manner we can easily construct the other 11 terms. There is a correction. PQ equals to 0 should be KPQ equals to 0. The matrix entry will be 0 if they do not belong to the same element. We get KT equals to F matrix equation system where this is your matrix capital K. This will be at the 12 by 12 matrix, 12 by 1 unknown displacement vector, and then we have the known right hand side vector. This is again of 12 by 1 size. So this is the load vector or force vector. So here we have 12 unknowns. Those unknowns, they are not associated with the superscript E. They will be T1, T2, T3, T4 up to T11, then T12. So for this is the first equation. P equals to 1 or first equation. Similarly, if we go to the last equation, then we get P equals to 12 or the last equation. So according to the numbering of the global equations that we make in the ID array, we get the global assembled matrix in which the equations are arranged. So we have 12 equations corresponding to T1, T2, T3, T4 up to T12. Now we already know that from the heat diffusion problem, the global matrix will be symmetric, it will be diagonal dominant, and it will be positive definite matrix. So this matrix can be conveniently solved using the direct methods or by using the iterative methods. So this completes the discussion of the construction of ID and LM arrays for a single degree of freedom in 2 dimensions. This can be extended for triangular elements or also for the higher order quadratic elements in 2 dimensions. Now we shall illustrate the construction of ID and LM arrays for problems with multiple degrees of freedom in 2 dimensions. To this end, we shall consider 2-dimensional Navier-Stokes equations for a simplified geometry with 3 unknowns per nodal points. Now, this is the example of multiple DOF case construction of ID and LM arrays in 2 dimensions. So we shall consider the Navier-Stokes equations of motion in 2 dimensions. The strong form is given by a steady state condition u bar dot del u bar equals to divergence of sigma plus rho f bar and divergence of u bar equals to 0. So these are the momentum and continuity equations in vector form. So momentum equation is written in the stress divergence form. Now we consider a model problem for which we deal only with the essential boundary conditions. So for this case, our degrees of freedom are the velocity vector and pressure, or u, v and p in 2 dimensions. So these are the primitive variables. The essential boundary conditions that we specify as u bar equals to g bar on gamma g. This is the EBC portion. This constructs the strong form of the flow equations. Now we consider the classic lead-driven cavity problem in 2 dimensions. The lead-driven cavity problem, it is an example of a recirculating flow. We shall use the primitive variable formulation and then we shall illustrate the construction of arrays. So this square box, this is filled with fluid. Here we have essential boundary condition at all 4 boundaries. So this is gamma g, this is gamma g, this is gamma g, and this is gamma g. So u bar dot del u bar, this is omega, equals to divergence of sigma plus rho f bar and divergence of u bar equals to 0 on omega. This is the omega portion, outer contour, the square. This is the boundary gamma. So for the left and right boundary, for the bottom boundary, we have the identical boundary condition. We take u is given equals to 0, v equals to 0, and pressure is unknown. Similarly, for the lower surface, we say these are the walls, rigid walls, and we have the no-slip boundary conditions for all the rigid walls. The bottom surface, we are having u equals to 0, v equals to 0, but we don't know the value of pressure. Similarly, for the left boundary, u equals to 0, v equals to 0, and p is unknown. At the top boundary, this is translating with u equals to 1, v equals to 0. Here also, p is unknown. So all the 4 boundaries are rigid boundaries. These are the no-slip boundaries. At the no-slip boundary, we have no-slip conditions for velocity and temperature. We are considering an isothermal flow problem, so it is only for the velocity. There is no slip condition for pressure, and at the wall, pressure is never a known quantity. Pressure has to be determined from the Navier-Stokes equations of motion. It means that for this particular case set of boundary conditions, pressure acts as unknown within omega and also along the boundary. So this is the physical problem which we have identified with respect to the boundary conditions and governing equations. Now we shall use the same set of mesh for this case using the same bilinear quadrilateral elements. So here we discretize the domain, that is the generation of mesh, discretization of the domain. So we shall discretize the domain using 16 elements and 25 nodes, the way we have done for the heat conduction problem. We shall follow the same mesh structure. So here we have elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So this is a representative finite element. This is the bilinear quadrilateral elements. It has the local nodes 1, 2, 3, and 4. Now I numbered the global nodes. Global node 1, 2, 3, 4. This is 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, then 16, 17, 18, 19, 20, 21, 22, 23, 24, and the final Lamin P node is 25th. So this is matching with the x-axis, and here we show the y-axis. So global node 1, it corresponds to the origin of the Cartesian coordinate system. This is a case of Cartesian structured mesh where every vertical line intersects every horizontal line one time. It means that we have two families of grid lines and this is a structured mesh. Okay. Now, for this case, we have number of nodal points equals to 25, number of elements equals to 16. Then we have number of element nodes NEN equals to 4 and number of degree of freedom per node equals to 3. So number of element equations equals to NEN into NDOF equals to 4 into 3. We have 12 equations per local element. It means that in the previous problem, it was a single degree of freedom. We have only one unknown per node. But in this case, we have 3 unknowns per node. So here we shall construct the ID array according to the coupled formulations. So there are two formulations while dealing with the Navier-Stokes equations. Coupled formulation and segregated or sequential formulation. In this case, I shall discuss the coupled formulation where we are using collocated arrangement of the primitive variables u, v and p. So we have 3 unknowns or 3 degrees of freedom u, v and p. So we construct 3 different meshes for every unknown. Should we have a different mesh for u velocity? Should we have a different mesh for v velocity? Or should we have a different mesh for the pressure? If we use different meshes for velocity and pressure, then we say that we are using a staggered arrangement of the primitive variables. But in our case, we shall use the collocated arrangement of primitive variables. It means that we shall have the same mesh for the velocity and pressure. It means that in our case, velocity and pressure, they will be present at every 25 node. So they are located at the same position. Because of that, we use the term collocated. Okay. So here it should be rho. So here this is the mesh which we already constructed, but to show in the chart, I redraw this. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the global node numbers. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and finally 25. So this is our x-axis, this is our y-axis, and this is the origin 0, 0. So these global nodes I identify with the dots. So these numbers, they are the global node numbers we already discussed for the heat transfer problem. And these are the elements E. So here we construct the IEN array, IEN AE equals to capital A. We use collocated arrangement of U, V and P, implying that we have the same mesh for U, V and P. So when we construct the IN array, this is like we have 16 elements. So E varies from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Then our small a, it goes from 1, 2, 3 and 4. So here we make the boxes for generating the capital A values. Capital A values are the global node numbers which are already indicated in the above mesh picture. Okay, so let us complete the box. 10, 11, 12. Now for the first element, the global nodes are 1, 2, 7, 6. 1, 2, 7, 6. For the second element, 2, 3, 8, 7. This is exactly same the mesh what we generated for the heat transfer problem. So for the second element, it is 2, 3, 8, 7. For the third element, it is 3, 4, 9, 8. 3, 4, 9, 8. For the fourth, it is 4, 5, 10, 9. 4, 5, 10, 9. For the fifth element, it is 6, 7, 12, 11. 6, 7, 12, 11. For the sixth element, it is 7, 8, 13, 12. 7, 8, 13, 12. For the seventh element, it is 8, 9, 14, 13. 8, 9, 14, 13. For the eighth, it is 9, 10, 15, 14. 9, 10, 15, 14. Next, it is 11, 12, 17, 16. 11, 12, 17, 16. Followed by 12, 13, 18, 17. Followed by 13, 14, 19, 18. Then 14, 15, 20, 19. Then for the 13th element, it is 16, 17, 22, 21. Then it is 17, 18, 23, 22. Then it is 18, 19, 24, 23, and finally 19, 20, 25, and 24. So here the terms in the boxes, these are the capital A terms or the global node numbers. So IN array, it is required for the mesh generation. Now we shall construct the ID array. So for generating the ID array, let us first go to the total number of nodes. So when we go for the ID array, our num_np equals to 25. Our SDOF, number of degrees of freedom per node, it is 3 for the collocated variable arrangement. So this is an element. We have 4 local nodes, 1, 2, 3 and 4. We have U, V and P present at all the local nodes. So we have U, V, P present in nodes 1, 2 and 3. So this is U, this is V and this is P. So we have, with this nomenclature, we have for this bilinear quadrilateral element for local nodes 1, 2, 3 and 4, we have U1E, V1E, P1E, we have U2E, V2E, P2E, we have U3E, V3E, P3E, we have U4E, V4E, P4E. So our element level equation, the element level equation will be of size n, number of element nodes into nodal degree of freedom. Number of element node is 4, nodal degree of freedom is 3. So we shall have a 12 by 12 matrix equation system for every element. It means that this Ke dE equals to Fe element level Navier-Stokes matrix. It will look like this will be a 12 by 12 matrix equation system. So this is Ke, this is Fe, and this is dE. So Ke is 12 by 12, dE is 12 by 1, and Fe is again 12 by 1. In dE, we shall have U1e, U2e, P1e. Then we shall get for local, this is for node 1, local node 1. Then we shall have U2e, V2e, P2e. This is for node 2, local node 2. Then we shall have U3e, V3e, P3e. This is for local node 3. And finally, we shall have U4e, V4e, P4e for local node 4. So, in this case, this is the first equation and element level equation, and this is the last equation. So, the first equation, this is the x momentum equation at local node 1 of element E. Equation for P, the last node is for equation for P. Equation for P represents the continuity equation. So this is the continuity equation at the fourth local node of element E. It means that out of 12 equations, we have 8 momentum equations and 4 continuity equations. So we have total 12 element level equations. This is constructed of 4x momentum. This is for UE plus 4y momentum. These are for VE plus 4 continuity equations. So small corrections here. This U2E, it is actually V1E, and the elemental pressure, we don't write it in this way, it should be PE. In terms of the degree of freedom, DE, then we can write it as D1E, D2E, D3E, D4E, D5E, D6E, D10E, D11E, D12E. So we are getting a 12th degree of freedom problem. This is the Navier-Stokes matrix. This is Ke. This is the degree of freedom vector De, and the right side load vector is Fe. So this is also a 12 by 1 vector. This is Fe. Okay. So now we have understood that numbering of the momentum and continuity equations for an element. So our numbering is like the local equation numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is local node 1, local node 2, local node 3, and local node 4. These are local equation numbers. Local equation numbers. The first one is for x momentum. The second one is for y momentum. And the last one is for continuity. So this d1, it is for x momentum, d2, it is for y momentum, d3 is for continuity, d4 is again for x momentum, d5 is again for y momentum, and d6 is for continuity. So like that, we construct the numbering of the element level equations. Now, let us see that how many equations we get, what is the value of maxi q for this present problem. So here, our num p equals to 25 and NDOF equals to 3. Therefore, total number of global equations expected equals to 25 into 3 equals to 75. Because of essential boundary conditions on u and v velocity, we shall have the less number of equations. Okay, so let us see we have how many essential boundary nodes. So if we look into this mesh, we see that we have 1 2 3 4 5 1 2 3 4 5 10 1 2 3 1 2 3. We have 16 essential boundary nodes. So we have b belongs to eta g equals to 16. Okay, so our internal nodes, this is 9. So internal or non-EBC nodes equals to 25 minus 16 equals to 9. Now, for these 16 nodes which are at the boundary, these 16 nodes which are at the boundary, we have only u and v velocities known and pressure is unknown. So, we can calculate the number of equations that we have to construct after the assembly. The number of equations equals to num p into NDOF. This is expected. Now, from here, we have the b values on the boundary. So, on the boundary, our NDOF values are specified only for u and v, but not for p. So, the number of equations that we have to subtract, that is NDOF minus 1 into the number of essential boundary nodes. Number of global equations after assembly equals to 25 into 3 minus 16 into 3 minus 1. So it is 75 minus 16 into 2, 32. So equals to 43. It means that maxi q, the maximum number of equations, equals to 43 equals to p equals to q. So here, now we are ready to construct the ID array. In multiple degree of freedom, we define the ID array for multiple DOF is defined as ID I comma a equals to p. Okay, so I index for DOF. For this case, our I is varying from 1 to 3. I equals to 1 for U, I equals to 2 for V, I equals to 3 for pressure. So we are giving the indices I for X momentum equation, Y momentum equation, and the continuity equation. So now we shall again, we require the mesh again for doing the numbering. 2, 3. So elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Then this is the first local node. At the first local node, we are given U and V velocities, but pressure is unknown. So the equation number indexing is 0, 0, 1. Okay, at first local node, our equation number indexing is 0, 0, 1. These are the global equation number. So for the second node, this index will be 0, 0, 2. For the third node, we don't know the pressure, 0, 0, 3. For the fourth node, global node, it is 0, 0, 4. For the fifth global node, it is 0, 0, 5. For the sixth global node, it is 0, 0, 6. For the seventh node, everything is unknown, so it is 7, 8, 9. For here, it is 10, 11, 12. Seventh node, eighth node, ninth node, 10th node, 11th, 12th, 13th, 14th, 15th, 16th, 17th, 18th, 19th, 20th, 21, 22, 23, 24, and finally it is 25. These extra lines, they are having no meaning. I just join it again. Okay, so for ninth node, it is 13, 14, 15. For the 10th node, it is 0, 0, 16. For the 11th node, it is 0, 0, 17. Then it is 18, 19, 20 at the 12th node. At the 13th node, it is 21, 22, 23. At the 14th node, it is 24, 25, 26. At the 15th, it will be 0, 0, 27. At 16th, it will be 0, 0, 28. Then it is 29, 30, 31. It will be 32, 33, 34, 35, 36, 37, 0, 0, 38, 0, 0, 39, 0, 0, 40. At 22nd node, 0, 0, 41, 0, 0, 42 at the 24th node, and the 25th node, the numbering is 0, 0, 43. So now we have the global equation numbers for and every global node. So here these are global equation numbers P or Q, and 2043, this is the maxi Q, the maximum number of equations, and 1 is the first equation. So this is the continuity equation. Continuity equation. This is X momentum. This is Y momentum. Now, if we construct the ID array, then it looks like A and I. I is 1 for X momentum, I is 2 for Y momentum, I is 3 for continuity equation. We have 25 global nodes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25. So this is 1, this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and finally we have here 25. So for the first case, for the first global node I equals to 1, equation number is 0. For the at the local global node 1, the second equation, degree of freedom 2, this is 0, and third is 1. So first one is for x momentum equation, second is for the y momentum equation, and third is for the continuity equation. So the next is 0, 0, 2, next is 0, 0, 3, 0, 0, 4, 0, 0, 5. For the sixth, it is 0, 0, 6. For the seventh, it is 7, 8, 9. For the eighth, it is 10, 11, 12, 10, 11, 12. For the ninth, it is 13, 14, 15, 13, 14, 15. For the 10th, it is 0, 0, 16. For 11th, it is 0, 0, 17. For 12th, it is 18, 19, 20. For 13th, it is 21, 22, 23. For 14th, 24, 25, 26. For 15th, it is 0, 0, 27. For 16th, it is 0, 0, 28. For 17th, it is 29, 30, 31. For 18th, 32, 33, 34. For 19th, it is 35, 36, 37. For 20, it is 0, 0, 38. For 21, it is 0, 0, 39. For remaining, all are EBC nodes for U and V. So we have only one equation. So it will be 0, 0, 40, 0, 0, 41, 0, 0, 42, and 0, 0, 43. So we have our ID array ready for numbering of the global nodes. Now we are left with the LM array. So now we shall construct the LM array. So construction of the LM array. We need this numbering of the equations again in this case. So here we redraw the mesh once more. So first mesh line, second, third, first, second, third. So elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and finally 16. The equations are 0, 0, 1, 0, 0, 2, 0, 0, 3 here, 0, 0, 4, 0, 0, 5 here. So here it is 0, 0, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 0, 0, 16, 0, 0, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 0, 0, 27. I should put in brackets. Then here 0, 0, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 0, 0, 38, 0, 0, 39, 0, 0, 40, 0, 0, 41, 0, 0, 42, 0, 0, 43. So now we have the global equation numbers in terms of the local node and element presentation. So now we construct the LM array. Okay, we have 16 elements. So for the 16 elements, E is varying from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Then we make the columns for every element. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and now this is for the last element. Okay. Here we have the local node number A. We have eth element, local node 1, 2, 3, 4. So here we have 1, 2, 3, the local equation numbers, 4, 5, 6, 7, 8, 9, and here 10, 11, 12. Okay. So for local node 1, this is local node 1. Then here we have local node 2, local node 3, and local node 4. Now at local node 1, I is varying from 1, 2, 3. At local node 2, I is varying again from 1, 2, 3. Local node 3, I is having 1, 2, 3. At local node 4, I is varying from 1 to 3. So I is the degree of freedom. I equals to 1, it means x momentum. I equals to 1 is giving you x momentum. I equals to 2 is giving us y momentum. I equals to 3 is giving us continuity equation. So here I equals to 1, 2, 3 we have defined here. So at the end we have a column for NEE or A prime or B prime. For the local node 1, first degree of freedom, A prime is 1, then it is 2, then it goes to 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It means that at local node 1, the first equation, it is the, for I equals to 1, it represents the first local node, local equation, or the first x momentum equation. Then we get the first y momentum equation. Then we get the first continuity equation. Then we move to the local node 2. Again, I varies from 1 to 3. Then we get the second x momentum equation, second y momentum equation, second continuity equation. So our arrangement of numbering is x momentum, y momentum, continuity, first node. Again, x momentum, y momentum, continuity for second node. We repeat it up to the last node. Now we use the numbering. We shall put the data from the LM array mesh picture. Okay, let us first make the chart. This is the final one for the last continuity equation. Now let us go for the first element. If we go for the first element, so for the first element, first local node, the equation numbers are 0, 0, 1. First element, first local node, the equation numbers are 0, 0, 1. First element, second local node, the equation numbers are 0, 0, 2. We just put 0, 0, 2. Now we move to the third local node. So the equation numbers are 7, 8, 9. So we simply put it here 7, 8, 9. Then we go to the fourth local node of element 1. We get here 0, 0, 6. So we get 0, 0, 6. Then we move to the second element. Now the equation numbers are 0, 0, 2, 0, 0, 3. For the third node, it is 10, 11, 12. 10, 11, 12. For the fourth, it is 7, 8, 9. 7, 8, 9. If we go for the third, it is 0, 0, 3. 0, 0, 3. 0, 0, 4. 13, 14, 15. 13, 14, 15. Then it is 10, 11, 12. 10, 11, 12. Next, we move to the fourth element. It is 0, 0, 4. 0, 0, 5. 0, 0, 16. 13, 14, 15. For the fifth element, it is 0, 0, 6, the first node. Then it is 7, 8, 9. Then it is 18, 19, 20, 0, 0, 17. If we go for the sixth element, it is 7, 8, 9. 7, 8, 9. Then it is 10, 11, 12. Then it is 21, 22, 23. Then it is 18, 19, 20. For the seventh element, it is 10, 11, 12. 10, 11, 12. Then it is 13, 14, 15. For the seventh element, then it is 24, 25, 26. Then it is 21, 22, 23. Next, we move to the eighth element. It is 13, 14, 15, 0, 0, 16, 0, 0, 27. And then it is 24, 25, 26. 24, 25, 26. Then we move to the ninth element. It is 0, 0, 17. Next is 18, 19, 20. 18, 19, 20. Then it is 29, 30, 31. Then it is 0, 0, 28. Now we move to the 10th element. So it is 18th, 19th, 20, 21, 22, 23, 32, 33, 34, then 29, 30, 31. For the 11th, it is 21, 22, 23. Then it is 24, 25, 26. Then it is 35, 36, 37. Then 32, 33, 34. Then we go for the 12th element. It is 24, 25, 26. Then it is 0, 0, 27. Then it is 0, 0, 38. Then it is 35, 36, 37. Next it is 0, 0, 28, 29, 30, 31, it is 0, 0, 40, 0, 0, 39. For the 14th element, it is 29, 30, 31, 32, 33, 34. It is then 0, 0, 41, 0, 0, 40. For the 15th element, it is 32, 33, 34. Then it is 35, 36, 37, 0, 0, 42. Then it is 0, 0, 41. For the last element, it is 35, 36, 37, 0, 0, 38, 0, 0, 43. Then finally, it is 0, 0, 42. Now, we have completed the construction of the LM array. Now, using the same method that we have shown for the heat conduction problem, we can construct the assembled matrix equation system. So let us see, we want to find out K11 from this matrix. So K11 for the assembled matrix equation system, this will be K11 equals to initial K11 guess value plus, let us scan for every element. Now this equation 1, it is present only in the first element, so there will be no contribution from other element. So when you go for K11, so this is a diagonal term. So for this case, P equals to 1, Q equals to 1. So P equals to Q equals to 1. This will give us A prime equals to B prime. We search it, A prime and B prime. This is equals to 3. So we are getting here K 3, 3 contributed by the first element. So this is coming from the continuity equation. Now we want to find out K19. So if we want to find out K19, this will give us K19 plus. Now let us search for 1 and 9 which are present in the same element. So 1 and 9, they are present together only in the first element. It is an off diagonal term. 1 and 9 together, they are not present anywhere else. So here P equals to 1 and Q equals to 9. For first element, P equals to 1 means A prime equals to 3. So it is giving us K, first element, A prime equals to 3. And for 9, B prime is also 9. So B prime is also 9 means it will be K19 equals to K19 plus K391. Now, if we want to find out, for example, F8, let us just try to find out F8. So we have to scan for global equation number 8 in every element. So if we go for the first column, first element, then we see that it is present. It is corresponding to A prime equals to 8. So this gives us F81 plus. Then you scan for element number 2. It is present corresponding to A prime equals to 11. So it is F11 2. Then you go for the third element. It is not present. Then you go for the fourth element. It is not present. You go for the fifth element. It is present for A prime equals to 5. Then we say that it is F5 5. So F5 5. Then again we scan. We go for the sixth element. So this is present corresponding to NEE2. So it is F2 6. Now if we scan for the remaining elements, 8 is not present for the other elements. Let us check it. Okay, so it is not there. Now these values, already I told that these values are actually capital P values. So now we have understood that for multidimensional problem, using the LM array, we can easily perform the assembly process. Okay, So here, if we see, I have told you KPQ will be 0 if P and Q, they don't belong to the same element, and easily we understand that there will be lots of terms where KPQ equals to 0, or this 43 by 43 assembled matrix will be certainly a massively sparse matrix. Okay, so now let us show the final structure of the assembled matrix equation system. So after assembly, we get KD equals to F, where this is the K matrix, and this is the D vector, and this is the load vector. This is the assembled matrix equation system. This is 43 by 43. So this is max AQ or P comma Q. This is the degree of freedom vector. This is the load vector. So this is 43 by 1. This is 43 by 1. So in this case, we have D1, D2, D3 up to D43. Now these D terms, they include U, V and P. It means that U, V and P all are part of the degree of freedom. This happens in a coupled formulation where we get a single matrix equation system. Coupled formulation gives single assembled matrix equation system for multiple DOF problems. So this D, it is a function of U, V and P. This contains U, V and P as per the boundary conditions. So this is the first global equation, the first global equation, and this is the last global equation. So if we go back to the LM array, then we see that this first global equation which we got, this is contributed by the degree of freedom 3, or it is contributed by the equation for pressure. It means that the first global equation, it will be the continuity equation. It will be the continuity equation. So we can say that D1 equals to P1E. Okay, so this D1 means it is P11. This is the first degree of freedom. Okay, now we illustrate the Navier-Stokes matrix for the same problem. We use a very coarse mesh using the same bilinear elements. So this is the lead driven cavity problem that we have already defined. Pressure is unknown at all the boundaries. Here we are showing the mesh with respect to 4 elements, and then we are showing one representative finite element containing the local nodes 1, 2, 3 and 4. Here we have shown the global equation numbers. So the first one is the x momentum, the second one is the y momentum, and the third one is the continuity equation. So we can see that at all the boundaries we have pressure as unknowns. So we are getting total 11 number of equations. Out of these 11 equations, one is x momentum equation, that is at internal node 5. Another y momentum equation we get at the same global node, and then finally we have 9 nodes from the continuity equation. Those are contributing to the pressure equations. And then here we are showing the LM array for assembly of the element level matrices and vectors. Our element equations are 12, and because of that here NEE or A prime or B prime, it is varying from 1 to 12. And then here we are showing the assembled matrix. So this is an 11 by 11 square matrix. Then the non-zero numbers, those have been shown by the black squares, and zeros have been shown separately. This structure clearly indicates that the Navier-Stokes matrix for the lead driven cavity problem, for example, it is structurally symmetric but numerically asymmetric. In this case we have 11 by 11 size or 121 terms, and it has been found that out of this 121 terms, 32 terms are 0. So around 26% of terms are 0. So this indicates that the Navier-Stokes matrix, like the heat conduction matrices we have seen before, is a sparse matrix. Now we are showing this matrix again with excluding the zeros. Okay, so here we are getting 32 zeros that I have mentioned you, total 121 terms, 121 terms. So percentage of zeros equals to 32 by 121. It is approximately 26%. Then we have 13 diagonals in this matrix. So this is a sparse and a banded matrix. This is an asymmetric matrix. I have indicated the main diagonal. In this matrix, the half bandwidth is 6. So in the first class, we have discussed about the half bandwidth. It is denoted by BW. Half bandwidth is 6 and bandwidth is 1 plus 2 BW. That is 1 plus 6 into 2. That is 13. In today's class, we have demonstrated the construction of ID and LM arrays in 2 dimensions for single and multiple degree of freedom problems. We have considered number 1, the Poisson equation for the SDOF case, and the Navier-Stokes equations for the multiple DOF case. For today's lecture, the textbook by T.J.R. Hughes will be extremely useful. Thank you very much for your attention.